Dear students, today we are discussing some useful results regarding Fourier integral. Okay, let us rewrite the Fourier integral as in a complex form. Okay, so how can we write the Fourier integral in a complex form? So that will be useful for the analysis. Okay, uh, let us consider f of x equal to integral 0 to infinity a of w cos wx plus b of w sin wx dw, where a of w is equal to 1 by pi into integral minus infinity to infinity f of v cos wv dv, and b of w is equal to 1 by pi into integral minus infinity to infinity f of v sin wv dv. We can substitute this a of w and b of w in the above equation. So you will get f of x equal to 1 by pi into integral 0 to infinity, again integral minus infinity to infinity f of v cos wv cos wx sin wv sin wx dv dw, right? So you can consider this is a trigonometric formula. Okay, cos a cos b plus sin a sin b, that is cos a minus b. So that formula can be applied here, and you will get f of x as f of x equal to 1 by pi into integral 0 to infinity, again integral minus infinity to infinity f of v into cos a minus b, that means cos wx minus cos wv dv dw. Okay, so cos is an even function, and suppose if what is that, and moreover f is not depending upon uh, w, because in the first f is a function of v only. Okay, so we can integrate the first integral with respect to v, and the integration outside the brackets is with respect to w. So we can represent, and moreover you know that with respect to v cos function is a even function. Okay, sorry, with respect to w, the function inside the bracket is a function of w only. That means after integration with respect to v, this square bracket, the term inside the square bracket will be what is that, function of w only. So and let us call this square bracket as f of w, and moreover you know that cos wx minus wv is an even function of w. Okay, and the function f does not depend upon w, and we integrate with respect to v, so we can integrate this function with respect to v. So this square bracket is actually capital F of w. Okay, and the range of integration of this square bracket function is 0 to infinity. Okay, since this is a even function, this will be an even function with respect to w, so we can say that instead of integral 0 to infinity, we can double this integration, and so if we double this integration, we have to divide by 1 by 2. Oh sorry, we have to divide by 2. So the entire function can be represented as half into 1 by pi into integral minus infinity to infinity, again integral minus infinity to infinity f of v cos wx minus w v dv dw. So half of this integral. Okay, because the function is considered as even function. Okay, so So what about what happens when cos becomes sine? Instead of we consider sine in this function 1, instead of cos, if we consider sine in this equation number 1, then this will be 0 because that will be odd function. You know, odd function integrated over minus infinity to infinity will be 0. So if we consider instead of cos, if we consider sine, this entire function will be 0. Okay, because sine function is a odd function. Okay, now you know the famous Euler formula in complex analysis. The complex analysis begins with this formula. You know, in this book itself you can see complex analysis. So complex analysis begins with this formula. In the introductory section you can see e raised to ix is represented as cos x plus I sin x. Okay, so instead of x we can consider wx minus wv. Then what happens? E raised to wx plus wv wx wv will be equal to cos wx plus I sin wx. Sorry, wx minus wv. Cos wx minus wv plus I sin wx minus wv. So f of if we multiply after replacing x with wx minus wv in e raised to minus x with f of v, we can see that f of v into, we can multiply with the f of v after the replacement. So f of v into cos wx minus wv plus I f of v into sin wx minus wv, that equal to f of v into e raised to, you know, that is e raised to I into cos wx minus wv. Okay, so that is available in the equation number 1. Okay, so using for that equation number 1, it is you can see here. Okay, no, in equation number 1 and 2 you can see, in equation number 1 and 2 you can see the term with the cos and term with the sine. Okay, so what will be the representation? So f of x can be represented as equation number 1 plus 2, 1 plus 2, equation number 1 plus 2, because since 2 is 0, the equation number 1 will be f of x, and this f of x equation number 1 plus 2 will give you, what happens, 1 by 2 pi, common for 2 times, integral common, f of e into cos wx minus wv plus f of e into sin wx plus wv minus wv dv dw. So we can add like this, 1 plus I into 2, 1 plus I into 2, 1 plus I into 2, equation 1 plus I into equation 2. So what happens? So that will result f of x equal to 1 plus I into 2 means f of x plus I into 0, that means f of x. Right side, when we add right side, first term 1 by pi into integral minus infinity infinity f of e cos f of e into cos wx minus wi plus I into 1 by 2 pi into integral minus infinity f of e into sin wx minus wv, but the second term is 0, you know, from equation number 2. So you can say that we have only first term. So f of x equal to 1 by 2 pi into integral minus infinity to infinity, integral minus infinity infinity f of v into e raised to I w x minus v dv dw. Okay, so this is called a complex Fourier integral. Okay, this is a complex number, you know. So this is usually called a complex Fourier integral. So sometimes we may have to use this formula for solving many problems. Okay, So what is Fourier transform? Now we consider uh, we can separate this exponential function e raised to iwx minus uh, iwv. So when we separate this e function, you can rewrite like this. Instead of 1 by 2 pi, we can write 1 by 2 pi into 1 by 2 pi. So 1 by 2 pi kept here, and another 1 by 2 pi push into inside of the first integral. Okay. So f of x equal to 1 by root 2 pi into integral minus infinity to infinity. 1 by root 2 pi into integral minus infinity to infinity f of v into e raised to minus iwv dv into e raised to iwx dw. Okay. And this function inside the square bracket is denoted by f cap of w, and is called Fourier transform of f. So we can just rewrite this as f of x equal to 1 by root 2 pi into integral minus infinity to infinity f cap of w into e raised to iwx dw, where f cap of w is equal to 1, the term inside the square bracket, that is 1 by root 2 pi into integral minus infinity to infinity f of x into e raised to minus iwx dx. Okay, yeah, this is the representation. Okay, so and it can be considered as inverse function of Fourier transform of f cap of w. Okay, this can be considered as inverse function because f of x is outside, f cap of w is inside. So but f cap of x is actually Fourier transform f. You know, this is the expression f cap of x. This is the Fourier transform of f. Equation 6. So what will be f inverse of f cap? I think you got the steps, with the idea of having these steps. Yeah, let us consider an example that will guide you to understand the concept in detail. Consider a function f of x equal to 1, and the range is mod x less than 1 and 0 otherwise. Okay, so what happens? What is f cap of w? Fourier transform f cap of w is nothing but, you know, the formula. You can use the formula f cap of w is equal to 1 by root 2 pi into integral minus infinity to infinity e raised to minus iwx dx. So when we substitute that value, you get, you know, that f of x is 1 for the region minus 1 to 1. So just put that value over that region and 0 in the remaining region. So f cap of w is equal to 1 by root 2 pi into integral minus 1 to 1 e raised to minus iwx dx. After simple integration, you know that will result in 1 by root 2 pi e raised to minus iwx by minus iw from minus 1 to 1, that equal to 1 by minus iw root 2 pi e raised to minus iw minus e raised to iw. Okay, so we can use the complex formula, that is e raised to iw is equal to cos w plus I sin w. So and moreover e raised to minus iw will be equal to cos w minus I. Instead of I we use minus I sin w. So what will be e raised to iw minus e raised to minus iw? That is simply 2i, just to subtract 2i cos w. So first term will get cancelled and the second term will become twice I sin w. Okay. Substituting this in the previous formula, okay, you can substitute here. When we substitute here, you can see that f cap of w is equal to root pi by 2. This 2 and this root 2 will get cancelled and just root 2 remains there. Okay, just raised to minus n I and I. Here we have one minus I and they have I, so it will become I by I is getting cancelled and minus n. Yeah, we can you can replace this as e raised to iw minus e raised to minus iw. So this minus 1 will get cancelled. Then 1 by root 2 pi is there. In the numerator we have 2. I get cancelled 2 sin pi. So what will be the? So I think this is in reverse position. You should have 2 above. Okay. So 2 by pi into root of 2 by pi. I think this is an error. Please check that. We should have root of 2 by pi into sin w by w. I think so. Please check that. Okay. And so this is an example of Fourier transform. Okay. Now let us എന്തായി നമുക്ക് നടത്തല്ലേ അന്നും മെസ്സേജ് ഇട്ടോ മെസ്സേജൊക്കെ ഇവിടെ ഉണ്ടല്ലോ ശരി so this is another example. Find the Fourier transform of f e raised to minus ax of f of x d. Okay, let us consider this example. What is f of e raised to minus ax? Just simply you can write it as 1 by root 2 pi into integral 0 to infinity. The region is only 0 to because the main region it is 0, so we consider only that region. 0 to 20 e raised to minus x e raised to minus iwx dx. So that is equal to, we can integrate that. You can consider this as a single function e raised to a minus a plus iw of x. So e raised to minus a plus iw of x divided by minus a plus iw from 0 to infinity. So after integration you can see that it is, after substitution, 1 by root 2 pi into so that is equal to 1 by root 2 pi into e raised to a plus iw. Okay, So this is we have considered 2 examples. You can consider more examples in the exercise so that you can get in touch with the Fourier transforms and Fourier integral, etc. And we will discuss this linearity of Fourier transform derivatives in the next class. Okay. So you can study up to this and submit in the Moodle platform today's class. Okay.